Okay, it should be working. Okay, so hi, hello. I'm going to talk about a project that we did on time series forecasting, actually time series modeling. Yeah, so I'm going to start by saying a few words about the project itself. So the project started a while ago, and during this year we conducted sort of a second iteration of this, adding a lot of new experiments and new baselines. So since April we have a preprint on arXiv, so we can read it if you want. Yeah, so we sort of move to the realm of time series, right? So for some of you it's not a very well-known domain, so you may be wondering, what is modeling time series like? Is it more like language? Is it more like computer vision? So basically it's sequential, so in this sense it's a bit like language, and it's not compressed, like the input is not compressed, it's not structured in any way. The input is raw, so in this way it's a little bit more like a vision, but in reality it's really like neither of those. Those time series data exhibit either some weird periodic patterns, yeah, the distributions shift over time. So really what it's most like, I would say it's like tabular data, but with some temporal dimension added. So let's review what's the problem. We are in the forecasting problem, so basically we want to model a joint distribution over some horizon given a certain context. So let's say we have 200 time series values and we want to model like 24 next ones. So we do it with this autoregressive models. So we basically predict one time step at a time and yeah, do regression here. And we are in the setting of univariate time series, right? So only one variate, only one feature at each time step, right? And so let's say a few words about what are the problems in the field, what are the challenges. So I was already talking about, well, the certain difficulty that comes with the variation across time series data sets. They can have many different patterns, they can exhibit different behaviors, and even inside one data set, well, the time series can be quite different, and over time they can also vary, right? They can be non-stationary. On this picture you can see like 4 very popular data sets, and those are the zoom-ins on certain smaller and smaller time frames. You can see that on a fine-grained scale they are sort of periodic, but other than that, some of those exhibit no like visible patterns. What's also important is that even if in this data set we have only one trajectory, right, only one observation from a certain stochastic process that sits underneath, in reality those are samples from a certain stochastic process, right, from a certain distribution. So we face this challenge of modeling the whole distribution given only one sequence, basically. Also, as I was saying, the time series can be multidimensional, and it also can happen, and this is the same case in a lot of sequential problems, that there might be some long-range dependencies in data. So also a couple of words about what has been done in this domain. So what's important to understand that like the progress in time series has not been that fast as in other domains like language or vision. So in the aspect of the usage of deep learning, I would say that time series are closer to what happens in tabular data, right? Even if we have some methods and they are successfully applied, then many people are still using like all good tools. So in tabular data, you may know that people still use XGBoost. In time series, it's still very popular to use like classical econometric methods to deal with the data, and those deep learning methods not necessarily like are better than them, right? So the domain has been lagging behind a little bit, but what has been done? Well, during the first phase of applying transformers, people were actually trying to find newer and newer ways to sort of inject the structural biases into those models, inductive biases into those models. So they were doing it by, for example, mapping the input into the frequency domain, very popular technique, or using the well-known decomposition of time series into the seasonality, that trend, and the noise. And yeah, what also turned out to be a good idea was also combining convolutions with the attention, right? To sort of extract this fine-grained patterns in data. But maybe one more word about the related work. Recently, there were also some papers trying to train foundational models in time series. So they were trying to teach models either using synthetic data or some mixtures of various data sets. Yeah, and some papers did it better than others, but they still lag behind the classical per dataset models. Yeah, so what's important, there was a lot of like overcomplication in those papers, and in our work we sort of try to, you know, cut all those additional extensions to the model and actually show that the simple vanilla transformer actually does a far better job at modeling those sequences and forecasting. So we basically used the vanilla transformer decoder, of course using the modern developments like GLU activation function or rotary embeddings. And we actually did one more thing correctly, that is, we used a discretization on those data. So various previous transformers didn't have this, were handling embeddings in different ways. So they were basically not vector quantizing the input data. They were just sort of either projecting it or repeating certain variates to fit the model hidden dimension. But they were basically operating on some projection of those data itself. One more observation: if you operate on raw data itself, it's hard to actually predict like the distributions on the output. Either you could parameterize the family of distribution that you are predicting, or do something like EQN, which you may know what it is or not. Yeah, so our method is actually, as I was saying, very simple. We take an input value, we split it into a fixed number of digits, in this case 3 digits, right? So we have 3 tokens. So you can think that the whole space of possible real values we sort of split into 1,000 possible values and then represent this one of those 1,000 quantized vectors as 3 digits, each digit being from the range from 1 to 10, right? And those digits have certain embeddings. And the number of those embeddings is actually lower than the number of embeddings that we would have if we embedded each of those 1,000 values separately. Yeah, so very simple method, not using all those fancy stuff. Another consideration is that since we are using this sort of autoregressive modeling of this whole horizon, and during inference we would be using Monte Carlo to sample the trajectories, then the consideration is like, wouldn't the estimation be worse and worse over time, right? Wouldn't the quality of data be far worse on the 24th time step of the horizon? So this image shows like very positive result. On the x-axis you can see the time step of the horizon. On the y-axis you can see the value. The red line here is a ground truth value, and those histograms here represent the empirical distribution of values at a certain time step. Empirical because we have sampled the trajectories using like simple Monte Carlo, right? And the those shadow blue things are the confidence intervals. One more thing about what we did correctly is we used a actually better way to measure the performance of our models. So as I was saying, due to the because of the distribution drift over time in the time series, it's not enough to, let's say, cut a time series at a certain time step and basically measure the ability of the model to predict a certain number of next time steps, just because we may have sampled a very easy cutting point with very little noise after it. So it's far better thing to do is use one of the very well-known and developed ways to backtest a model, which basically means that we train and evaluate our model on 100 different time windows, evenly distributed across the time dimension, right? So we, of course, avoid the leak from the future to the past by training on some prefix of this window and evaluating on some sort of a suffix. And what we have found is that our very simple approach outperforms certain well-known transformer models on all 4 data sets which we're considering. Just a bit of clarification. Those are not like the newest models. I think patch TST has 1.5 years at this point, but it's like fairly recent. Yeah, and not all of those are stochastic models. Some of those are deterministic models, and we compare our method on deterministic metrics in this table, just to show that even if our goal is to model the whole distribution, our model is still better at, point-wise predictions than deterministic models. Same story on stochastic metrics. QL is quantile loss, which you may know from quantile regression, and CRPS is like the average of quantile losses on different quantile levels. Of course, those metrics have their drawbacks, so they are not perfect. So to measure like the true properties, the true stochastic properties of TSGT, of our approach, we also try to approach the evaluation using more a principled approach, and that was to use well-known statistical tests to basically test if the model models the certain quantiles well, right? The tails of the distribution. So what the Skupiec test does, we basically, for each time step in the horizon, for each specific time series from the data set, we check how many times in those 100 windows predicted value is higher than the ground truth. Basically, how many times we wrongly overestimate the 95th quantile, right? And yeah, we can compare it against the perfect method. Let's say the perfect method, assuming all those stochasticity, would have a few times overestimated this quantile. So yeah, so we basically test if this is done correctly, and this percentage value denotes how many of those statistical tests each approach passed on a certain data set. On this picture, you can see those values. Basically, the green pixels represent the past tests, and red pixels represent the tests that we didn't pass. The x-axis is the index of the time series in the electricity data set. And on the y-axis, we have both the quantile levels and horizon steps. Okay, so what's the conclusion? The conclusion is that we model all those stochastic properties, like most of those stochastic properties we model better. Our performance decreases with the level of the quantile, so it makes sense that it's harder to model higher and higher quantiles. So while our model does well on the stochastic benchmark, metrics, it also does well on those deterministic ones, outperforming fairly modern transformer methods. And yeah, so the time is up, so I'm going to skip the ablation part. Thank you very much for listening.